Okay, shall I start? Okay, I will make a start then, if that's okay with you, Violet.
Yes, sir.
So what I'm going to do today is present a case study of converting a calculation-intensive application to make use of multiple CPU cores using Tickle threads. And the immediate question might be, why would you do this? And the reason is simple, that low-cost multi-core processors are becoming more common, and it would be good to make use of them. The context for this is an application called the 6MC Platform for Hospital Performance. Now, just confirm if you've got the second screen, the screen that's got an equation in the middle.
Yes.
Cool. I was a little paranoid after everybody else had trouble sharing the right screen. So 6MC is a US health industry startup. There's a couple of ticklers involved. There's myself and Dave Roseman. Several domain specialists who are mostly medical doctors and hospital managers. And the goal of 6MC is to help address this equation, the healthcare equation. So the cost of healthcare is a function of the quality of the healthcare and the access to that healthcare. The challenge is how to increase the access without compromising quality or cost. 6MC was formed to address this challenge by automating the knowledge of the domain experts and by providing tools to apply that knowledge to enable relative hospital performance analysis. The architecture of the platform is a bit like this. Essentially, the US public health data records are mined along with client and other data. The health records are imported, they're corrected. There's a lot of anomalies, multiple sources use different schemas and so on. Additional measures are derived and then they're scored. There's about 300 million measures per year to sift through. A word on scoring: sometimes higher is better, such as with quality. Sometimes lower is better, such as with mortality or costs. And scoring is a way to enable apples to apples comparisons of those. It also allows identification of outliers in the data. The result of this is data for 6,700 hospitals, 2,200 measures per hospital per year, 10 years of data. And then we provide multiple views on the data for different audiences. TCL/TK is used throughout the platform. In the data mining part, we use Tickle CSV from Ashok Nadkarni that reads CSV files very, very fast. We use John Roll's extension XLSX for reading Excel spreadsheets. We also make good use of Alexander Skope's read and write OOXML to read and write Excel. Thanks, Alex. I really appreciate your work there. The database is SQLite. In the user interface, we make extensive use of TableList and from TableList from Charbonemity, and also Aryan's plot chart. For deployment, StarKits, and the plan is to use PTK as well, almost certainly with a TK renderer, but if there wasn't HTML CSS renderer, we'd certainly look at that. I'll just show you some screenshots to give you an idea of what it does, and then we can look at where we need to speed up. This is a picture of the one of the screens. We've already chosen a hospital to investigate. That's the Advocate Good Samaritan down in Grove, Illinois. You can see there's 3 types of views here: board and management, clinical, and patient. And this screen is for selecting the comparison hospitals. In this case, we're selecting short-term acute care within 20 miles, and that results in 16 matches, we're also specifying explicitly a couple of competitors. If you look down the bottom, I don't want to dwell on this too much, but you can see there's many other criteria we could use. And the core of this screen is actually table list. Once the hospital is selected and the comparison hospitals are selected, we can then look at a high-level performance comparison. We have a hierarchy of measures, so those 2,200 measures per year are organized into a hierarchy. At the top level is a single measure, total domain performance, or total performance rather. Then we have 5 domains and then 22 categories, but you can drill all the way down to individual performance measures. Color is used to indicate relative performance. So the green boxes, the performance of this hospital is within 1 standard deviation of the mean of the comparison hospitals. The blue boxes, this hospital overperforms, and the orangey colored hospitals are underperforming. And for those old TK people here, that's background is BEASC. I had to get it in there. And in this case, we can very quickly see that quality, and in particular inpatient processes, demands our attention. And at this point, you would then drill down through the hierarchy, which I'll skip, but you'll end up at the lowest level where you can actually look at actionable data. In this case, we've drilled all the way down into emergency care. We can see that, for example, a specific issue here, the time before admission of our hospital, we're investigating 314 minutes in the emergency care department, I should say. 340 minutes waiting, whereas the top 4 hospitals vary between 214 and 225. So there's some actionable data. Also, this is table list at the top, and that's plot chart at the bottom. Okay, back to the overall architecture. I'm going to talk about deriving and scoring, which is where our main bottleneck was. So the rules for deriving and scoring are specified in an Excel database using a little language which is almost Tickle. The rules are specified by domain experts. Excel actually turns out to be a reasonable user interface for them, and we have programs that read the Excel and do the hard lifting. So this is turned into some Tickle formula, pretty much a one-to-one, and then stored in the SQLite database. The first solution to calculate do these calculations, scoring calculations, was to use the Tickle expression command. So in pseudocode, for each hospital, for each year, for each measure, basically set the value of the measure to be the evaluation of the formula as stored in the database. So for each measure, for each year rather, load the starting measures from the SQLite database, perform the calculation, save them back in. But it's not quite that simple, because the model, the formulas are defined in a spreadsheet. We have to accommodate forward referencing. And so we can do up to 6 passes over this data. Quite a bit of calculation, potentially over 800 million calculations, 67 hospitals, 10 years, 6 passes, 2,200 measures, plus all the database activity. So pros and cons. The pro of this approach was it was quite simple to implement, but the con is it was incredibly slow. On my notebook, it took 24 hours from go to woe, and that effectively stopped me using the laptop while this was happening. Why was it so slow? Firstly, there was no compilation of formulas. Each formula was being evaluated for each hospital, for each year, for each pass. It also may have been that the formulas were being byte coded each time, but to be honest, the inner workings of byte coding within the EXPR command are beyond me. I'd be interested in Donald's and Kevin's opinion on that. But if it was being byte coded each time, that's worse than no byte coding. There was also sequential processing. There was no parallel execution of calculations, no overlap between calculations and database access and storage. But despite all of this, it wasn't initially a problem. The public data only arrives every three months, so we only have to recalculate every 3 months. I just left the thing running over a weekend. But then we started to refine the model, and we wanted to be able to add new formulas or new rules and change rules almost daily, and we wanted to incrementally test those changes. So the next solution was to get a separate computer. At least that would keep my laptop free. At first I looked at cloud computing, but it turned out it was quite expensive due to our storage requirements. We have terabytes of data to process, and it wasn't really a practical thing to sort of spin up a cloud computer, upload terabytes, and then shut it down again. I happened to be talking with Richard Hipp about some other stuff, and Richard mentioned he'd got a AMD box and was using it for SQLite fuzz testing, and Richard was very positive about that. So it got me thinking, and on the chat one day I asked for opinions about Intel versus AMD for running Tickle. Sergey Brest had already run some tests, and as you'd expect, Sergey had some strong opinions on this, and his impression was that he could recommend AMD processors, mainly because of the size of their level 3 cache. As Sergey put it, due to reference counting, almost all Tickle operations will hit the level 3 cache, and so more level 3 cache meant better performance, and the AMD had much more cache than the equivalent Intel processor. So I ended up putting together a box with an AMD Ryzen 3900. That's 12 core, 3.8 gigahertz, so 1.5 times the clock speed of my laptop. More importantly, it had 64 megabytes of level 3 cache as opposed to 16 on the Intel. And this, as of the middle of this year, this was AMD's top desktop processor. They have released this, or announced a 16-core one last week, which would be even better. They do make 64-core and higher processors, but those things are 10 times the price of these. So the performance, this brought it down to 12 hours. Same code half the time. It was faster than I expected given the 1.5 clock speed ratio, but we're not talking apples to apples comparisons. The memory speed and disk speed were much faster on the new box. But at least now I could run it overnight. It didn't clog up my laptop, and I still had 11 cores to use. Which takes me to the third solution, which was to actually compile the formulas. And to do this, just generated a procedure for each formula. That's 950 formulas, roughly half of our measures are derived, and 11,000 lines of code were generated. It was pretty simple. This gives an example which is equivalent to the earlier example, where the formula is just turned into a procedure, and it's byte coded once, used many times. And for simplicity here, I've omitted the variable definitions, but we actually found that the fastest way to access the variables is basically upvar them into a namespace. Perhaps that's due to the byte coded commands accessing local variables directly. So the elapsed time on this was 2 hours, 24 hours to 12 to 2. And I could have actually stopped there and been quite happy, but I had another 11 cores to use, and how best to do that. There's a couple of ways I could go about it. Pardon me. The first way, obviously, I considered using multiple processors. This would provide complete separation from each instance, and potentially they could run, well, potentially they would run on a separate core, but they could even run on separate hosts. To enable this to happen, I would need to use SQLite write-ahead logging, so I could have one writer process and many readers. And then I just use sockets or name pipes to do the inter-process communication. And that definitely would have worked. In fact, this is how the wiki is implemented. But it would have required me to perform some re-architecting to introduce some job and queue management. So I then had a look at threads. I've been itching to use multiple threads for a while. And these provide almost complete separation due to the tickle apartment threading model. So interpreters run in a single thread. There's no need for mutexes. If you've ever had to work with mutexes, you'll understand why that's a good thing. And the tickle thread package provides an inter-process communication API, a thread send API for message passing. So threads at this level are almost like processes. However, threads offer one compelling advantage, and that is Threadpools for managing the workload. Threadpools were originally implemented by Zoran Vasilovich. They are now part of standard tickle threading support, and they provide a work queue abstraction. You create a thread pool, you specify the number of threads, you specify initialization code for each thread, create as many jobs as you want by posting to the thread pool, and the thread package manages the workload for you. So your program just has to wait for the results. This meant there was minimal re-architecting on my part. Just split the source code into two files, one for the main thread and one for the worker threads. The main thread, as I've indicated here, creates the thread pool, posts the work to the queue, waits for the results as each job completes, and then saves the results in SQLite. The worker threads, well, on startup, the worker thread, when it's passed a job, I should say, the worker thread which has SQLite open read only, it will get the formulas from SQLite, and it'll get the initial values for the measures, and then it performs the calculations and returns them to the main thread, which in turn writes them to the database. Now, my particular application here is particularly well suited to using thread pools, and the work units I use is one job per hospital. The reason for that is that some of the measures I need to guarantee the processing order, because they do 1 and 5 year changes. So one job per hospital, it then calculates in order all the year's values. And by the way, we have to recalculate them all the time, because the data coming from the government records may be changing history, if you like. It's not uncommon to have the data from a couple of years ago to change. So one job per hospital. After each year, the results are returned to the main thread, which writes them into the database. Then after the last year, the worker notifies the main thread, so the progress can be recorded, and then just waits for the next job to be allocated to it by the Threadpool package. A very high-level overview of the way you do this in the main program, in the main thread, I should say. You get the ID of the thread, which will then be passed to the worker so it can send the response back. You create the pool for each hospital, it then posts, and then it does a wait for each job to complete. So the items in white are basically the 4 API calls you need to make. And there also needs to be a save procedure, which is called back from the worker thread. In the worker thread, it's just simple. For each year, you calculate that you delete the namespace that holds the variables first of all, so there's no bleed from year to year. You load the new values from SQLite, do the calculations, and then send the results back to the main thread to be saved in SQLite. Performance. Well, the elapsed time dropped to just over 10 minutes. So we've gone from 24 hours to 12 hours to 2 hours to just over 10 minutes, which I think is more than acceptable. The optimum amount seemed to be using 11 threads on a 12-core processor. That kind of makes sense. The Ryzen itself, the 3900, has 24 virtual threads, but going beyond 11 made no difference at all. And I think the reason is the virtual threads don't actually give you any more processing power. They just reduce the context switch time between cores. I ran some tests and I pretty much established that the SQL write performance was not the bottleneck. So I worked out I could actually double the number of calculation threads if more cores were available. Arjen, just notice what Arjen said in the chat. Yeah, at least 3 cups of coffee for me. I'd really like to get it to single figures eventually, just because, and I could certainly do that by buying the new CPU that's been announced, but I could look at critical to generate C code. I could look at quad code to compile it. I could certainly change the algorithm. There's no reason to iterate 6 times for each measure. I could just do it for those that contain forward references, and then only till it stops changing. The tool chain is interesting. Sergey mentioned that there are GCC flags to get native compilation options. I haven't used those yet. And A and B also have their own C compiler available, which I could look into. There may be some Linux configuration options to help with the specific workload. I probably will have a look at that. And I could overclock, because this particular CPU is very easy to overclock, but I'd rather not. And I would love to figure out how to use a GPU from Tickle someday. But basically, I've gone from 24 hours to 10 minutes, and that's good enough for me. Right, conclusion. I'll borrow the phrase from Tom Radcliffe at Active State in a paper he wrote, which is still on their website. Tickle threads are threads done right, and I have to agree with him. I like to put it that tickle threads are threads for mortals. And in my experience, that Threadpools do make life much, much easier. It took me about 1 day to convert this application to multi-threading and testing. So in summary, multi-core support from Tickle is not rocket surgery, and we all should be doing more of it. Thank you, and I will hand out. Let's have a look if we've got any questions here. Oh, we have lots of chat. Have we got any questions? Ron. So the question is, did I chart performance as a number of threads, and are they tailing off or still going linear with threads when I hit the core limit? It's linear till the core limit, and then it just flattens, makes no difference after that. And I use the nproc command to work out how many threads to create. Let me see, another question. Andreas said I'd have done the expression compilation before buying better hardware. It wasn't just a case of getting better hardware, it was a case of getting it off my laptop so I could do other things. But yes, in hindsight, maybe I should have done that. I've got a question from Andreas Caprese. Number of CPUs, yeah, there's a bunch of ways of doing it. I just use the nproc command. Have I missed any questions? I'm looking. Oh, hello, there's a whole lot more. No, I didn't have to build a custom SQLite, Sean. I just used the standard SQLite that, actually I used the standard one that was on, what am I running on that thing? Ubuntu, I think. Do I have any, Daniel Bodan, do I have any performance problems with large amounts of data in a table list? Nope. I haven't hit that limit. I noticed Rene was up to 80,000 and it seemed pretty responsive to him. So I haven't hit that limit. Richard Hips asking, how loaded up does the cooling fan get while it is running? Surprisingly, not much. The cooling the cooling in these Ryzons, it's just, they come with this huge cooling fan. And since I've got 4 minutes, I'll tell you an anecdote. I hadn't built a PC for maybe 10 years. I'd been using Mac gear, and the guy at the PC shop asked me the question, do you want RGB memory? I said, what? RGB memory? Apparently you can pay $30 extra and your memory changes colors under load. And then they tried to sell me some water cooling, but the Ryzen comes with a very big fan, which does a great job. Lots of questions, lots of discussions about CPUs, detecting CPUs in the chat. Any other questions? Okay, well, slightly ahead of time, but any other questions, hit me up in TK chat or email.